In the very first part of this question, we are trying to analyze the rate of change of the amount of C, which is represented by dx dt. And to conceptualize the idea of rate of change, or to conceptualize the differential equation for this particular question, I'm going to make use of the schematic that I have introduced on the Achevas TV theory outline, and that is to try analyze the system. So I'm going to draw a little box here, which is going to represent dx dt. So I'm going to try to read the question to see at every unit time how much goes into the system, and at every unit time how much comes out of the system. Because by adding this and subtracting this will give me the overall rate of change, which is going to represent dx dt. So if you were to look at the question, the rate at which the amount of C increases, so this is where we see our rate of increase. It is proportional. Okay, so it is going to be k times of the product of the amount of A, which is A minus X, and B minus X, which is the amount of B. So B minus X. This is going to be the rate of increase. But according to the question, I don't see any rate of decrease in terms of X. So I'm going to assume it to be 0, which means that for this case here, dx dt is equal to the rate of increase, A minus X, then B minus X, and minus 0, which I guess I'm not going to be writing that. And since we are talking about rate of increase, and this k is the constant of proportionality that I've introduced, so I'm going to go for a value of k that is bigger than 0. So this represents the rate of increase. And since the question says that B is equal to A, so I'm going to write this down here. Since we know that B is equal to A, that means dx dt, it can also be written as k times of A minus X times A minus X, which is going to be A minus X squared. So this will be the differential equation relating X and T. And the next thing that we are supposed to do is to solve this differential equation. So the next thing that I'm going to do in terms of solving is to bring this over to the left-hand side. So we will have now A minus X to the power of minus 2 dx dt. This is equal to k. And integrating both left and right-hand side with respect to t, on the left-hand side, I'll be getting this. So integration of this, then minus 2 dx is equal to k integration of 1 with respect to t. This is an easy integration. So it is going to be A minus X to the power of minus 2 plus 1, it is minus 1, divided by the coefficient of X, which is minus 1, and divided by this power, which is also minus 1. This is equal to kt plus an arbitrary constant. I'm going to go for A to be the arbitrary constant. So this is 1 over A minus X. And this is equal to kt plus A. Let's try to solve for A. And the question gave me this piece of information. The question says that there's no traces of C found at the start of the experiment. So the start of the experiment tells me that T is equal to 0. And since there's no traces of C found, that means X is equal to 0. So I know this piece of information. When T is equal to 0, X is equal to 0. So I will have a 1 over A minus 0 is equal to 0 plus this arbitrary constant A. So I guess A is equal to 1 over A. So 1 over A minus X. This is equal to kt plus A, which is 1 over A. And now let's try to express X in terms of T. So it will be A minus X is equal to 1 over, and this I'm going to write it as kt plus 1 over A. So making X a subject, X is going to be equal to A minus this. Let me just re-express the denominator by grouping this together, which will get me a 1 over akt plus 1 divided by A. So we will have A minus A over akt plus 1. Let's group this into one single expression. So that will be A times this, which is going to be A square kt plus A, then minus A divided by the common denominator, which is akt plus 1. And now we will get our expression of x in terms of t, and that is a square kt divided by akt plus 1. And what we are trying to be sketching here is going to be one that is of a rational expression. Why is this a rational expression? Because if you were to look at the numerator, a and k, they are constants. So the numerator is a linear polynomial. It is the same for the denominator. Since a and k are constants, so we have another polynomial. So we have a improper rational expression. So for this kind of rational expression, according to what we have discussed in the theory outline, there's going to be a horizontal asymptote. You can either do a long division to deduce the equation of the horizontal asymptote, or by observation, I know that the equation of the horizontal asymptote will be x is equal to a square k. Basically, it's just taking the coefficient of t divided by the coefficient of t, which helps me to come out with the equation for the horizontal asymptote, which is x is equal to a. So let me sketch in this horizontal asymptote. So we have this, where the vertical axis is x and the horizontal axis here is t. So x is equal to a, which I'm going to label for this horizontal asymptote. And if I were to let a and k be numbers so that I can press it into my calculator to get the rough shape of the graph, for example, you can let a be equal to 1 or k equal to 1. I'm going to get a shape that is something like this. Okay, that's actually supposed to be a vertical asymptote. But I'm going to just sketch the part of the graph that is t is bigger or equal to 0. So I'm going to start from here. My graph will be tending towards the horizontal asymptote this way. Okay, and since it can be bigger or equal to t, I'm going to use a solid dot here. And let me finish off by labeling my graph. So x is equal to a square kt divided by akt plus 1. And now we are given that when t is equal to 1, x is equal to half a. Let's make use of this to solve for k in terms of a. So when t is equal to 1, we are given that x is equal to half a. So a square k times 1 divided by ak times 1 plus 1. This is equal to half a. And there's a on both left and right hand side. So I'm going to cancel away one of the a's. So now I will have here in the numerator ak. For the denominator, I'm going to cross multiply it over. So we will have a half ak plus half. So if I were to shift this back to the left hand side, you will be getting a half ak. So this is equal to half, which means that k is equal to 1 over a. And this helps me to find an expression for x that is going to be in terms of a and t. So it is a square k, which is 1 over a, t, divided by ak, which is 1 over a, t plus 1. So it is going to be at divided by t plus 1. And now we have x in terms of a and t. We should be able to solve for what of question 1, which is the time needed for x to be equal to 4 over 5a. So when x is equal to 4 over 5a, that means it is when at divided by t plus 1 is equal to 4 over 5a. And since there's an a on the left hand side and another a on the right hand side, we can cancel it. So we have a t is equal to, cross multiplying this, 4 over 5t plus 4 over 5. Bring this back to the left hand side, 1 over 5t. This is equal to 4 over 5. This tells me that t here is 4 hours. And now we are looking at a case where b is less than a. But for the rest of the condition, they are going to remain exactly the same. So I'm going to be making use of the same schematic as what we have used in part 1 of the question, except that I'm switching k for h since we are looking at another question. So dx dt is going to be a result of the rate of input, which is h, a minus x, multiplied by b minus x. And the rate of output is 0, so I'm not going to write that. And h here is going to be a constant that is bigger than 0. So we have already come up with now the differential equation relating x to t. The next thing that we are supposed to do, let's solve this differential equation. So I'm going to shift this over to the left hand side, dividing this across. It will be giving us a 1 over, then I have a x minus a minus x multiplied by b minus x. So I have this dx dt. This is equal to h. And I'm going to be integrating both left and right hand side with respect to t. So on the left hand side, it is going to be integration of 1 over a minus x multiplied by b minus x. Then dx, this is going to be h integration of 1 dt, since h is a constant. To integrate this, there are two strategies, two possible manipulations that we can do before we can conduct the integration. The first one will be to make use of partial fraction, and the second one will be to expand this and try to do a completing square to the denominator. I'm going to go for the partial fraction strategy, but you can definitely try completing square. You're going to be getting the same result. So for partial fraction, just to keep my solution a little bit cleaner, I'm going to just write it here, okay? So I'll be letting this, which is 1 over a minus x multiplied by b minus x. I'll let this be equal to p over a minus x plus q over b minus x. And to solve this partial fraction quickly, I'm going to make use of the cover-up rule, which I did mention in the Achevas TV theory outline. So to find p, we will be covering up a minus x, and I'll be letting this x here be equal to a. So it is going to be 1 over b minus a. And as for q, I will be covering up b minus x, and I'll be letting this x here be equal to b. So I have a 1 over a minus b. So we have a b minus a minus b. So to synchronize, I'm going to factorize out negative, and this will be 1 over a minus b. So we have a minus b and a minus b. It is probably going to be easier for us to work with. Oh, and the reason why I chose an a minus b is because since b is less than a, so a minus b is going to be a number that is positive. So maybe it is going to be easier to work with. Maybe it is going to be helping me to reduce any possible careless mistake. But anyway, it doesn't really matter. You can also go for a b minus a. But I'm going to go for a minus b. So I will be able to re-express this now as p, which is minus 1 over a minus b multiplied by 1 over a minus x. Then plus q is this. So it is 1 over a minus b multiplied by 1 over b minus x. So I have this dx, this is equal to h integration of 1 dt. And since we have already prepared for coefficients that are going to be similar, like for example this case, I can now factorize out 1 over a minus b. So this is going to be integration of minus 1 over a minus x plus 1 over b minus x dx. This is equal to h integration of 1 dt. So this is going to be 1 over a minus b. And for this is going to be minus ln of modulus of a minus x. But let's just take note, a minus x and b minus x, they're actually positive numbers. How do we know that? Because a minus x, b minus x represents the amount of substance a and b. So that I mean, the nature of it, already implies to us that they must be positive numbers. So instead of going for a modulus of a positive number, I'm going to go for just a curved bracket of a positive number. So I'll have this divided by the coefficient of x, which is minus 1. Similarly, since b minus x is positive, so I will use a normal curved bracket. I will have this divided by minus 1. So this is equal to ht plus an arbitrary constant. I'm going to go for b since I've already used a in part 1. So this is going to be 1 over a minus b. This is ln of a minus x, then minus ln of b minus x. This is equal to ht plus b. I'm going to group this together using the law of logarithmic function. So it is this a minus x divided by b minus x. And I'm going to multiply a minus b across to the other side. So it will be a minus b ht plus a minus b times b, which is getting a little bit big in terms of its expression size. So I'm going to just replace it by another arbitrary constant, c. And this c here represents a minus b, b. I'm going to remove this ln from the left-hand side. So a minus x divided by b minus x. It is equal to e to the power of this, which I can also rewrite it as e to the power of c multiplied by e to the power of a minus b h t. So a minus b h t, it is this. As for e to the power of c, I'm going to rewrite it and replace it by just another arbitrary constant d. So d e to the power of a minus b ht, where d here represents e to the power of c. And I guess I'm ready to solve for this arbitrary constant, which have been accumulating from one expression to another expression. You can definitely solve for this arbitrary constant later, but I think here is a good time for us to do that. And I'm going to make use of this piece of information. It is the same piece of information that we have used in part 1, which is at the start of the experiment, there are no traces of c, which means that when t is equal to 0, x is equal to 0. So I'm going to make use of that. When t is equal to 0, x is equal to 0. So we will have a minus 0 divided by b minus 0. This is going to be d e to the power of 0. E to the power of 0 is going to be 1. This tells me that d is going to be equal to a over b. So now I can have an expression relating x to t, and in terms of just a, b, and h, which I've defined previously. So we will have a minus x divided by b minus x. This is equal to d, which is a over b e to the power of a minus b h t. I'm going to divide this across to the other side. So I have a minus x. Dividing this across, that will be b over a e to the power of minus a minus b ht. This is equal to b minus x. And multiplying this in, it is going to be this times this. So it will be b e to the power of minus a minus b ht. This multiplied by this. This is going to be minus of x of this. So b over a e to the power of minus a minus b ht. This is equal to b minus x. And I'm going to bring all the x over to the same side. So I'm going to bring this over to the left-hand side, which will give us an x minus x of is b over a e to the power of minus a minus b ht. So it is this is equal to b minus b e to the power of minus a minus b ht. Let's do another simplification, making x the subject this time. So x is going to be equal to, factorizing out b, we have a b of 1 minus e to the power of minus a minus b ht. So we have this. And this is going to be divided by, since I've already factorized out x, so I'll be having a 1 minus b over a e to the power of minus a minus b ht. Let's do one more simplification because this just looks a little bit weird, right? So let's multiply by a in the numerator and the denominator. So in the numerator, we will have this as ab of 1 minus e to the power of minus a minus b ht. And the denominator, it will be a minus b e to the power of minus a minus b h t. And in this last part, we are going to be analyzing the amount of c, which is x, after a long time. That is when t tends to infinity. So when t tends to infinity, for x-wise, it is going to be a, b, then 1 minus this. And since a minus b is bigger than 0, and h is also bigger than 0, so when t goes to infinity, the power here becomes a very negative value. So e to the power of a very negative value will be 0. So we have this in the numerator. And as for the denominator, it will be a minus. This will also become 0. So we have this, which means that we are going to be left with a ab divided by a. So when t tends to infinity, x will tend to b.